Hello and welcome. So today what we are going to look at few of the questions from K nearest neighbor, and apart from this I have already solved few of the question from SVM, few of the question from knife base, few of the question from I think linear regression, and few of the question from uh, trade-off between the base or variance. So you will find the separate playlist for this where we are solving the or we are practicing few questions from the machine learning, so that you can refer. There are not too much question, but there are few questions are there, so if you wish you can refer that. Okay, so now let's look at this KNN questions. The first question is k nearest neighbor is dash algorithm. So we have given this parametric, non-parametric, Agar and lazy. So that's the first point, is that this is lazy algorithm. Why? Because at the test time it takes too much computation, right? If we have large number of data, then it is going to calculate the distance, all of the distances, right, from the test point. So all of the distances from that k value, if k is very large, then it is going to compute all those distances. And during and even so even the point is that it takes longer time during the test time in comparison to learning time. So its test time is going to be greater than the learning time. So that is why we call it the lazy. And even if you increase the number of k, that that then that computation time is going to increase and algorithm is going to be slow. So that is why we call it the lazy. And this is on non-parametric. Why? Because the data are from some unknown distribution and we don't have much info about the parameter of this unknown distribution, like the mean and variance, all these things. So this is the non-parametric and lazy algorithm. Now let's look at this question number 2. You have given that following two statement, then you will have to look at this, which one is correct and which one. So statement 1 is, in case of very large value of k. So very large value of k means you will have the large neighbors, right? So maybe you will have some large neighbors. So if you take something like that, so these are the positive class and maybe some negative class are there also here. So you can take some few neighbors, right? So for this k is equals to 3. And if you take this large neighbor, right, so maybe k is equals to 15 here, right? So that may happen that include the points from other classes into the neighborhood. So other classes points are getting included in this neighbor, right? So that is correct statement. And in case of too small value of k, the algorithm is very sensitive to noise, right? So let's suppose that there are few negative classes here. Let's say there are two negative class here and three positive class here. So due to noise, it may happen that it may appear uh, it may appear that it is not the neighbor of the test point, right? So due to noise, the decision may change due to noise, that due to variation of this data point, right? Because if it has some noise, that it may appear or somewhere here that is not in the neighborhood of this data point. And what would happen, that let's suppose that this one also have some noise and that may appear here, that is out of its neighbor, from out of the neighbor, right, of the data point, of the test data point. then the decision is going to be that this will be classified as a negative, right? Because these two negatives are there and one positive are there. So so you see that due to noise, the KL that and in case of if this is too small k, right, so this is not going to capture lot of neighbors, right? And if it has the large k, then you see that even if there are few variation with these all data point, but still we have the large number of the positive classes in comparison to negative classes. So even if we have some few noise and few variation in this data point, ultimately the test point is going to be classified as the positive. But if we have some small and in a small k, if we have some noise that have some kind of variation, then it may appear that it so the decision is going to the classification is going to be wrong, right? So that is the overall point. So that is why this statement is also correct, and you can say that both are true. Okay, let's look at this question number 3. State whether true or false. You have to look at for true and false. So KNN algorithm does more computation on test time rather than the training time. So I explained you, right? So what happened at the train time? So train time you have to do nothing. You have to just uh, maybe you have to just store the vector, right? Store the coordinate, or you can say store the what is the vector, just store it at the train time. And during the test time, what you have to do, you have to calculate the k distances, right? So the first point is that during the test time, you will have to look for the k nearest neighbor, right? And you are going to see that 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 k nearest neighbor, and from that k nearest neighbor, which class is greater. I mean to say that here if you see that three positive class are there, right, and two negative class are there. So if you are looking at five nearest neighbor, then three are the positive class, then ultimately it is going to be classified as the positive class. So the main point is that during the train time you have to do nothing, that you have to only store these vectors at what position they are. And during the test time you will have to calculate the k distances, and in k distances you will have to look at those classes, like which class they fall, right? So this is the true statement. Okay, let's look at this question number 4. Suppose you have given the following images. uh, uh, One represents the left image, two represents the middle, and third the right one. Now your task is to find out the value of k in KNN in each of the images shown below. Here k1 is the first, k2 is the second, k3 third figure. So if you look at closely the image, you see that let me so this region, you look at this region. So now this region is uh, so what is happening, that you see this yellow one. So what is happening, that you are increasing the value of k, right? Because this blue class is going to be include, and here it is going to, some blue classes are going to include. So what you are doing is the increasing the value of k. So if this is k1, this is k2, this is k3. So look at this region only, then you will able to see. So here that k3 is greater than so k3. So this is the value of k in this sequence. The value of k is going to, so k1 then k2. So correct answer is C. Now look at this question number 5. Which of the following necessities feature reduction in machine learning? Okay, so irrelevant and redundant features. Which of the following necessities feature reductions of how you can reduce the features? So irrelevant and uh, redundant features, so you are going to neglect those. Limited training data, so if you have limited training data, that way you can reduce the uh, features, right? And limited computational resource, so all of the above, the correct answer for this all the. Now let's look at this question number. Next question, that you have given the following data where x and y and two input variable and class is an uh, dependent variable. So we have given this, right? One, and at what class they belongs to. So what class they belong to, what class they belong to, and what class they belong to, and we have given this the plot. Let me, so these are the positive one and these are negative, right? So suppose you want to predict the class of new data point at x is equals to 1 and y is equals to 1 using Euclidean distance in 3 so k value is 3, and which of the class. So first of all, let's mark this uh, 1 1, right? So here it is 1 and y is 1 here, so the your test data point is going to fall here, right? Now you will have to use the Euclidean distance and in nearest neighborhood. So the nearest neighborhood going to be these three, right? So all these three are the positive class, right? So it is going to be the positive class. So the correct answer for this is A. Okay, now let's look at this question number 8. Suppose we are using dimensionality reduction as a pre-processing technique. So like dimensionality reduction, so PCA, that is principal component analysis, is the one of the technique that you can reduce the dimension by, maybe you can look at the feature vector or the features that are dependent to other features, then you can neglect that feature. So there are various techniques that you can neglect, you can reduce your dimension of the features. Suppose we are using dimensionality reduction as pre-processing technique, that is, instead of using all the feature, we reduce the data to k dimension. So here we have given that k dimensions, right, with the PCA, principal component analysis, and then using this PCA projection of our features, which of the following statement is correct. So choose which of the correct. A, higher value of k. So here k is the dimension, right? So higher value of dimension means more regularization. So regularization, if you look at, so it basically penalizes the you can say so but if you are adding the regularization term, that means the main point is to add the regularization is to have the less or it is to uh, some kind of neglecting the some dimensions, right? So higher value of k means more regularization, higher value of k means more regularization, higher value of k means less regular. So that means higher value of k, so k is here the dimension, right? So if we are considering more dimensions, then obviously we will have the uh, less regularization, right? So higher value of k means less regularization, right? And if we have more regularization, that means we are penalizing some of the or maybe features that we don't want to consider much. So the correct answer for this higher value of k means the less regularization. Less regularization. Okay, so this correct answer is B. Okay, this question number 9 in collaborative filtering based recommendation. Also, so this is the practical example, so you do not have to worry about this. So in collaborative filtering based recommendation, the items are recommended based on the similar user and similar items. So both of these. So correct answer for it is both of the above. So you will have to look at this, but it's collaborative filtering. So this is the practical example. So basically, in collaborative filtering, uh, uh, so it is kind of hybrid. So hybrid, I mean to say that let me just explain you and give you an overview that you we have two kind of recommendations. One is based on the interaction between two user. So what does happen that suppose I have seen some movie A B C, right? So let's say the user A have seen, or let's say user you have seen some A B C movie, and user you2 have seen some B C movie, right? So based on the so these two users are very similar, right? And let's suppose say a user 3 have seen this D movie, right? So these two users have the very similar taste, right? So what I can do is I can recommend this user 2 to this movie A, right? And how we can calculate this? We can take the uh, Jacobian similarity that we call the intersection, right? If you look at this intersection, then BC is the common part, right? Then what, and maybe it has seen some movie D that user U2, then what I can do is I can recommend this movie A to user U2 and this D to user U1, right? So this is how that the similar user kind of things work. And this similar item means those what you have seen earlier, right? So maybe if you are searching a car in car marketplace, and maybe you have seen some uh, brand that BMW, then based on your filter that that algorithm is going to recommend that some same BMW of different model. So that is the similarity. So that was all from this KNN, right? So you see that what we are doing here is also the nearest neighbor, right? So there are a lot of things that there are a lot of way to calculate the distance between two things. That is the point. Okay, that is all from this video. We will look more question if I found. Okay.